So, what it's going to do is it's going to bring you to the WebMO Job Manager. This is where completed jobs and jobs that are running can be found, right? So I was trying some of these out. Initially, we're going to be doing calculations that only take a couple seconds. Later on, when we're trying to get more and more accurate values, they're going to take minutes, hours, hopefully not a day, but the research that I do, some of these calculations can take a month. So, yeah. Okay. So, the way that we would make a new molecule, and there is a link or on that sheet that I gave you, down at the bottom, and I will post I think this is either already posted or I will be posting it on our Blackboard site. But the address down at the bottom has a guide that you can use to refresh your memory on how to do all this stuff. Okay. So there's this new job. Click that, and you can either import a job. We will eventually be also using Gauss View. It's a program that companies, if you ever are doing computational work for a company, that's the program. Most of the time that's the program they're going to use. There's two really big ones. There's WebMO, and there's three: Spartan, WebMO, and Gauss View. The Spartan and Gauss View are really expensive. We have a license for Gauss View. So WebMO is also expensive, but so we got two of the three. But the Gauss View is the most widely used. Okay, so you can import those jobs from one of those other programs into here, or we can make our own by clicking on Create New Jobs. On the left-hand side, this is sort of your icon tool menu. There's also ones up here for doing a bunch of stuff. We will just start out by making a molecule. So here, there's a thing that looks vaguely like a periodic table in the upper left. If you click on that, it brings up a periodic table. And so this is how you select the different elements that you want to make. You can think of this kind of as a molecular model kit, and this would be pulling the ball out of the rack. Right? So you pull the ball out and you build your molecule one atom at a time. So if we want to make drop down a carbon, that is a single carbon atom. If I want to make a carbon-carbon bond, I will click on where I want the bond to start, drag where I want the bond to end, and that will add the new carbon. If I want to make a double bond, then I click on where I want the bond to start, click on where I want it to end, and that makes a double. Triple, same idea. You can go through all the different type of bonds. Right? If we want to add, let's say we wanted to do ethanol, right? You can do that to add the oxygen. Okay, so there's a couple different ways of adding hydrogen, right? Hydrogen, it's the last thing that you do. So we could use our periodic table to add the hydrogen atoms, right? And so click, drag, right? Or there's two places. We could either use this broom-looking thing, which will clean up the structure to an idealized geometry. The wrench-looking thing uses molecular mechanics to come up with an optimized structure. Both of those will look at your molecule, and any place that it looks like it needs an extra atom, like there's a bond that needs to still be formed, right? So this carbon has 2 bonds, it needs 4. It will add hydrogens to fill those numbers, right? So if we click on the wrench here, there we go. It added the 2 hydrogens, and you can tell that the bond distances also shifted. I had the carbon-carbon double bond a little bit longer. The carbon-hydrogen bonds are a little bit shorter than what they actually are. So it uses this process called molecular mechanics. We might touch on that at the very, very end of the class, how that actually works. But uses that to make the molecule. Okay. Now, some of the things we can do with this, without doing any sort of calculation, like forcing it to do heavy calculations, we can look at the symmetry operation. So if you've taken inorganic chemistry, you might be familiar with symmetry operations, mirror planes, rotational axes. If you haven't taken inorganic chemistry, when you take organic chemistry, you go, from PChem. We don't need it all that much. But essentially what this is showing, in terms of symmetry, there's a mirror plane that bisects the molecule. So if you take one half and imagine it reflecting over to the other side, you get back what was there before, right? So essentially there's a mirror that cuts right through the molecule, and that is where it is located. Okay. We can also look at the orbitals. So these are the molecular orbitals as opposed to the atomic orbitals. So the most stable one would be the sigma bond between the, looks like the oxygen, sort of the orbitals of the hydrogen, oxygen, and carbon coming together. Now these are listed from most stable to least stable. Right, so the HOMO would be the highest occupied molecular orbital. On the far right here, this OCC is the occupation. Right, so this has 2 electrons, 2 electrons. These all have 2 electrons, so the HOMO, highest occupied molecular orbital, is the last one that has electrons. Right, so we can look at that, and that's what that one looks like. The LUMO, the lowest energy unoccupied molecular orbitals, would be the first set that don't have electrons. So that would be this one here. Ends up looking like that. Okay, you might have, do you guys remember these from organic? We touched on HOMO, LUMO in organic chemistry. I haven't taught organic chemistry here, so I don't know. Yes? Oh, did they do HOMO, LUMO there? Okay. So this is essentially a way to visualize those orbitals. Essentially what the orbitals partially tell you is where's all the electron density, which tells you where things are going to attack, whether it be a cation or an anion, right? We can also look at some of the properties, and these properties are based on molecular mechanics calculations, which are fairly low level. They're not all that accurate, but in terms of where the electrons are at, it does a decent job. So we can look at, we already looked at the HOMO and LUMO. We can look at the electrostatic potential, which is essentially the charge density of the molecule. Right? So what we would expect is that the oxygen has the highest electron, the highest negative charge, and then the hydrogen that's on the oxygen would have the highest positive charge, right? Because that hydrogen-oxygen bond here has the greatest dipole moment, right? And so what we see is that the alkene part of the molecule is all roughly a greenish shape, so it is similar, it's kind of isoelectric, right? The whole thing has about the same charge density, but here, where you got the oxygen, has a big negative charge, where the hydrogen has a big positive charge, right? So the cations are going to be interacting with this side, anions are going to be interacting over here, okay? So let's say we wanted to do a calculation, and we're going to be doing this next week. This little arrow to the right, and again, next week, we'll be going through this all again, right? So I'm just getting you prepped for it. Next week when we actually go through it, we'll go through each one of these steps again. But in the interim, you can actually go onto that site as long as you're on campus, or if you live off campus, you can establish a VPN, virtual private network, If you're not sure how to do that, email me or swing past my office and I can show you how to do it. Okay. So click on this little arrow which says continue. Okay, that's fine. Okay. And next time when we're actually doing the lab, I'll go through what all these different settings mean. We'll do a bunch of calculations using different settings and see how that adjusts the numbers, right? So what is, well, first thing first, the job name, all it's gonna do initially is take the chemical formula and call that the job name. For our class, probably what we'll do is have that and then dash your initials so that you can find it, or maybe we'll start out with your initials dash and then the chemical formula. That way we can order it by person and you can pull the jobs that you were using. Not 100% sure which one we're gonna do, but probably using your initials so that you can find your calculation will probably make it easier. Okay, calculation here is the calculation type. Whole bunch of different options. So the first one, molecular energy. This is with the bonds, the bond distances, how they're currently set, and the bond angles, how they're currently set. What's the energy of the molecule without adjusting anything, right? So what's the amount of energy in the interaction between all the protons, neutrons, and electrons of the entire molecule, right? Where they currently exist. The next one down is geometry optimization, and that is essentially do that molecular energy calculation, and then based on that and the forces that it's experiencing, make adjustments to try to find the lowest energy. So adjust the bond distances, bond angles, and dihedral angles to come up with the lowest energy configuration. Now when it's doing that, it's not, it doesn't know chemistry, like intuitively like we do. So it's using math to find a minimum. So it's looking for the derivative in the energy, it's essentially going downhill. Why I say that is, if you're doing a geometry optimization, it will find the local minimum, the minimum energy of the structure that is the closest to where you start. It's not going to necessarily find the absolute lowest energy structure. If you remember back from your organic chemistry, if we look at propane, right? You have the anti and the gauche arrangements, and the energy as you rotate. So if this is CH3, this would be your anti arrangement. We call these hydrogens. Then the energy in anti, so 180 degrees between them, starts out at the minimum. Looks something like that, right? Where these here are when the methyl group here is in the gauche arrangements, right? So jog memory, yeah. So if you start out having a structure where instead of your methyl group here, instead of being in this location, it's maybe over here somewhere, it's not going to rotate past that eclipse geometry to go to the anti. If you're starting out somewhere between these 2 points, it goes downhill, and so it will end up at that geometry. Okay, so what this means is when you make something up, you got to use a little bit of your chemical intuition to say, does that structure look close enough to what I think it's going to look like? Am I starting it out and will I be finding a local minimum, or am I actually going to find the global minimum? We're going to play around with some stuff where there's a couple ones that'll trick your chemical intuition, so we're going to do that doing what's called a conformational analysis. So essentially we're going to do something that looks like one of these plots. We're going to make a plot like that, and we're going to show the one that your chemical intuition says is going to be the lowest is actually up here, and the real lowest one is a different configuration. right? And so one of the things we gotta do when we're doing these calculations is not necessarily trust fully our chemical intuition and try all the different configurations to make sure we find the actual global minimum. Right? Because if you're looking to see like the enthalpy of a reaction or the enthalpy of formation for like butane, right? If you calculate the amount of energy, the stability of the butane molecule in this gauche arrangement versus the anti-arrangement, you're going to be off by, what is it, like 3 kcal, something like that. And so your numbers would be off, right? It's not the actual enthalpy of formation for the molecule. We typically take the enthalpy of formation as being the most stable structure, right? So it's something we got to take into account. Okay, so that's the second one, geometry optimization. The next one is vibrational frequencies. So vibrational frequencies is taking the structure that you have. What are the vibrational frequencies? The bond stretching, the wag, the asymmetric and symmetric stretches. If you've had analytic chemistry, you might have heard of those before, or maybe in organic chemistry when they're talking about IR spectra, you know, the CH stretch, the CH bend, right? So that's what these frequencies are those modes. Your CH stretch, CH bend, OH stretch, right? We can calculate what those are going to be for any molecule that we want, right? So we can actually calculate an IR spectrum without having to synthesize the molecule and run it in, you know, an IR. Okay. Next one down. So the vibrational frequency. That one doesn't adjust the structure. It will just take the structure that you gave it and calculate the frequencies. The next one down is a two-part calculation. First, it optimizes the structure, and then it does a vibrational calculation, right? Most of the time when you're doing vibrational calculations, this is the option that you do. But if previously you already optimized it, there's no need to optimize it again. Once it's optimized, right? So if you previously optimized it, you can take that structure and then do a frequency calculation on it. If it's a new structure, the one that you just made up, you should do an optimization and the frequency calculation combined together. It's just other options, right? So you could do geometry optimization, save that file, use that to do a vibrational frequency calculation, or you can select this other option and just do them both at the same time. That by far is more generally what happens, but you can do it either way. Excited state UV vis, and we'll be doing those later in the semester when we're talking about energy excitation and, you know, UV vis spectra. NMR, so we can calculate the NMR. That's going to be way towards the end of the semester. We'll actually talk about how NMR work on the atomic scale. When we're doing that, we'll do some calculations there. Right? So essentially, all these are different types of calculations that we can end up doing. Okay. So if we just select, let's say, geometry optimization and frequency calculation. Now, there are different theories and basis sets. When we start talking about Schrodinger's equation, we're going to talk about what it means by basis set. Right? For now, it's just how many functions are you giving it. Right? So this is the calculations are approximating other equations or where the interactions between the electrons and the nuclei. Right? And the more functions that we give it to account for those interactions, you know, whether the charge distribution, the ability of the orbitals to bend and stretch, and be, if you think of p orbitals, right? So p orbitals normally have, you know, a shape that's completely vertical axes, but when they're actually bonding, those orbitals can bend, right? So if we just give it the functions that describe the straight linear fashion, it's not going to do a good approximation of the energy. So if we give it additional calculations or additional functions which allow the p orbitals to bend a little bit, then we'll get a more accurate representation of the molecule. Right? So that's essentially what these basis sets do is they give additional functions to the calculation to take into account flexibility in the actual molecule. The reason why we don't just go, say millions of different functions is it has to solve each one of those equations, right? So the more functions you give it, the longer it's going to take. And so one of the other exercises we're going to do is we're going to take a molecule and just ramp up the functions one after the next, write down how long it took, and the relative energy. So we're going to get an idea of calculation cost versus accuracy, and sort of the happy medium. At what point should we stop? Right? At some point, you're going to get more accurate than your experimental results, and so there's no need to keep going because you can't verify it that it's actually the true value compared to experimental if your experimental has huge error bars. Right? The theory, there are a bunch of different ways of using those functions to calculate the energy. Some of them are parameterized for different types of molecules. So some of them might do better for charged species. Some of them are better for hydrocarbons, right? And so we gotta select the theory that we're gonna use. Some of these theories also involve more complicated equations, and so they would take longer to calculate. So again, we'll go through a lab in which we're looking at the different theories, how long it takes to calculate, and the relative accuracy. So for those, we're going to pick one basis set and then play around with the different theories and see how accurate it is, and then how long it takes to calculate. And then the last one is the charge. So on the molecule we were working with, there was no real way to say, did we already pull off an electron? Did we put on electrons? Is it cation, anion, or neutral? Right there, the charge is where you say it's a cation, anion, or neutral. Right, we can say +2, -2, +1, -1. We're going to enter that in. And then the multiplicity, if you remember from probably general chemistry, when you had your orbital diagrams with the arrows up and down, right? That's the spin multiplicity. If they're both paired, it has a spin multiplicity of 1. If you have a radical, which, have you guys done radicals? You're aware of what a radical is? Okay, that's when you have an unpaired electron. So it can either be spin up or spin down. So it has a spin multiplicity of 2. And then if you have 2 electrons in different orbitals that are both pointing in the same direction, it has a spin multiplicity of 3. We will get into all that when we get into those orbital discussions later on. All right, so I'm just trying to familiarize yourself with what all the different boxes are. For a lot of them, it'll just be, cookbook, do this, fill in that, come up with the calculations until we've covered all that other material. Okay. Then you click on continue, and it will run the calculation. So running. It actually doesn't take very long, but the web page doesn't refresh, every single second. So this one took 27.1 seconds, and then we can either look at the file itself, what that looks like. So you can either click there or on the blue link for the name. So this is what it optimized to. It might look fairly similar to what it started out as. Molecular mechanics does a fairly decent job. The bond distances and the bond angles likely tweaked by a couple of %. Right, so probably not much that you'll be able to see visually, but if you were actually go in and measure the distances, it would have changed. Okay, now the information that we're after is down. So we scroll down. This has a whole bunch of different information that we are going to use later. But the interesting stuff, I think, is if we click like here, animate, we can actually see the different vibrational modes, right? So this would be a rotation of the 2, 3, so the C2, well, technically that's the first carbon, but the numbering that we have for this molecule that we made, atom 2 and atom 3, it would be a rotation of the bond. You can take the molecule, and if we look up here where it's like a curved arrow, that allows us to rotate the molecule around. So we can rotate it, look down that bond if we want, look at it from a different angle. You rotate it around. The next one is translate. So if we wanted to move that off to the right to build, maybe we wanted to see hydrogen bonding between ethanol and water. So move the ethanol over to the side, and then we can add in a water over here and look at the interaction between the two. Okay. Then there's zoom in and zoom out. Moving up, zooms in, moving down, zooms out. If you're making really large molecules, you can zoom in on a specific area, fiddle with it, and then zoom back out. This program actually, if you select the correct parameters, you can actually start modeling some proteins. But don't do that until we get more familiarized with methods and basis sets, because you can tie up the server for months otherwise. Okay, so we can stop the animation. We can go down, look at other vibrational modes, or here we can click and it'll actually show that's what the IR spectra should look like for that molecule. Okay? So, this is what we're going to be doing next week. Questions? Joy? Any questions? Okay. So over the weekend, if you want, you can log onto the site, make some molecules, play around with it. Sort of familiarize yourself with making molecules. We will be doing it again next week, right? But if you want, if you're talking about molecules in a different class, make up the molecules, look at the vibrational modes, see what they look like, just play around with it, okay? It is now your sandbox to use. Okay. Okay, so derivations. We had been before we start up, do you guys have any questions from what we covered on Tuesday?
As for the ultraviolet catastrophe,
Mm-hmm.
the implication slide number 20, I think.
Yeah.
So the first one, why should all objects should rapidly go to 0 Kelvin? Like, cause it says.
Oh, yeah, so if everything's giving off energy, right, and by the first law of thermodynamics, energy can't be created or destroyed. If they're constantly throwing off photons, or light in the form of energy, then they're continuously losing that energy, and so they should cool down. And so everything should rapidly go to 0 Kelvin because it's throwing off all the thermal energy that it has in the form of light. Okay? Yeah, either this is the case, or we've just found something that creates infinite energy. Right? So energy has to come from somewhere. The objects would quickly go to 0 Kelvin because they would dump off all their thermal energy in the form of light. But they don't. Okay. So we had been deriving the Riley-James equation. Yeah, in terms of what I expect, I don't expect you to be able to do these derivations. It's more of, in the book, it says, you know, according to classical physics, this is the equation you come up with. It doesn't explain why that's the equation, right?
So what should we like concern ourselves with, like knowing the theory behind it?
Sort of the method behind it, right? So using a conceptual view of something and then using that to derive the math.
So how would it be on our tests?
Your tests are going to be more of some of the applications of these things, like the de Broglie wavelength, right? So here's an object moving at a particular speed. What's the wavelength associated with it? For what would be on the test or homework or any sort of thing, place you should be looking is under these learning objectives. So these are the things you're going to need to be able to do, right? They do not say, you know, derive the Rayleigh-James equation or any of that. Being able to take integrals, do derivatives, those are going to be important because that's how we apply the Rayleigh-James equation. Well, we don't apply the Rayleigh-James anymore because we got Planck's law, which fits things better. So for example, given two of the following, determine the third. If you got the mass, speed, determine the wavelength, or given the wavelength and the speed, determine the mass of an object. So that would be the de Broglie wavelengths, which are based on math and speed. We're going to get to that maybe today. So this is the photoelectric effect. We're going to talk about Einstein's interpretation and how that works, but once you have the equation, how do you actually get the results? So given the threshold frequency, determine the work function, and then the kinetic energy that comes off if photons of a particular wavelength are hitting the surface. Later on, a lot of it's going to be the stuff that we get to in a bit, which is the wave functions, valid wave functions. We're going to be doing deriving a particle in a box, particle on a surface, particle in a three-dimensional box. So from that, it's deriving particle in an object. So you need to be able to use the general technique that we were using for deriving the end equation for these particular shapes to derive it for a different shape. When we get to it, it will be a little bit more clear on how to do that. Okay, but these are the things that you'll be expected to sort of know how to do. And if you read through the book, do the homework problems. The first homework problem set, I'm going to try to get it out either tonight or tomorrow. And it will be due, well, I'll figure out a decent time when it's going to be due, but it won't be due for at least 2 weeks. Okay. Yeah. So unfortunately, you know, this chapter is fairly large, but essentially chapter 7 is going to be the first exam. First exam is just going to be chapter 7. This lecture is going to be chapter 7 is broken up into 2 parts. Essentially what used to be chapter 7 and what used to be chapter 8, but in the new book, it's all chapter 7. Okay? Most of the questions that are going to be related to this stuff will be hitting possibly next week. We're talking about operators, eigenfunctions, if something is Hermitian or not. I in no way expect you to know what those words mean because that's why you're taking the class. Okay, we will get into what all that stuff is as we get to it. It is totally doable. It will make sense when we get there. Okay? And then knowing what these are the terms that we're going to be learning in this the first part of the chapter. And so essentially what you'll want to do or what I would recommend doing, flashcards, write out the definitions and just memorize. Okay. 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 So. I believe we actually got to the point where we had this should actually be more of a new, so that's the energy density based on frequency. Boltzmann's constant, frequency squared over C cubed. Right? And where were you guys having your notes? Okay. Now, the Rayleigh-James equation itself has this being 8 pi frequency squared kBT over C squared. Okay, so the question I think that we had at the end is where is that C, the difference in C coming from, right? So if we look at the units on this, right, 8 and pi have no units. The Boltzmann constant is joules per second, or sorry, joules, not per second, joules per Kelvin. Temperature has Kelvin. The frequency is 1 over seconds each one. We have 2 of those. Divided by meters per second to the 3rd power, right? So our Kelvin cancel each other out. We got inverse seconds to the 2nd power here, inverse seconds to the 3rd power. So this is going to cancel out all but one of those seconds. So we'd end up with joules seconds meter cubed. I have no. I have a straight unit in there. Yeah, sorry. I think I dropped a unit here. There we go. Okay. So the first one, we were calculating the energy density. That's the energy per unit volume. What the equation that we were graphing before was the amount of energy coming off of a black body. Right, so the Rayleigh-James, this over here was intensity, and this was, we could either graph wavelength or frequency with high and low being opposite directions, right? So this is intensity. That's actually, the term is flux. So that's amount going past a surface per unit time. So what we have here from this one, if we take the derivative of this with respect, so what this is one is showing is the amount of energy in a unit volume, not how fast those energy units are passing the surface area of the volume. So essentially what we're talking about is, this top one is the amount of energy in the box. What we're graphing over here is the amount of energy that's going through the back wall. Right? And so the difference between those two would be, so this is A, B, C, your three lengths. This is A and B. The difference is how long this part is. And because we're talking about light, that's traveling at the speed of light, and so that distance is going to be C. Right? And so that additional C term down here comes from that distance. So when we're talking about this equation here, we're interested in the flux, how much energy is making it, essentially if you're standing in front of a black body, how much is hitting your surface area at a time, not how much is filling a volume. So that's where the difference between the C here and that C there come from. Okay? So that's why it's to the second power. Going between the two is a bit more lengthy of a mathematical thing than I actually want to go into. Okay, so it's essentially where the difference comes from. Is that sufficient? That's where the difference is. Okay. Now, in your book, there is another representation for the Riley-James equation. So this is energy per unit frequency. If we look at energy per unit wavelength, because there ends up being an integral, there's an additional term that gets thrown in. It works out to be, and it's a related derivation wavelength to the fourth power. Okay, now what we had said is that the reason that Riley-James, was thought to be a fairly decent approximation, or have actually been used for a while, is because down at these really long wavelengths in the IR, at certain portions of the IR in radio wave region and the microwave region, it fits really well. It in fact fits pretty well spot on in the microwave range, right? So any equation should, as our wavelengths go to infinity, as our wavelengths get really big, you should see this equation. Right? This equation fits the data spot on for really long wavelengths. For short wavelengths, it does a terrible job. Right? If we look at, so this here, this is actually our 0. If we look at the experimental results, what we find is that as our wavelength goes to 0, our energy density, or our intensity, also goes to 0. Right? Experimentally, what we find is if we look at the really, really short wavelengths, there's essentially no light there. Right? So what that tells us is we need an equation that should fit these two things. As it goes towards infinity, I goes to the Riley-James equation. Right? Seems to fit that equation fairly well at those long wavelengths. Okay, so what Max Planck did, and for this part, we're going to reuse a large portion of the derivation we did previously. So, you guys got your notes from the previous one before? Okay. essentially we're going to take, so I'm gonna keep this so that we have this as being our goal, for as the wavelength goes towards infinity, we should get back this equation. Okay? If you look back through your notes, there was a part where we had derived the number density, D capital N. All right, that was right before we said, according to Newtonian physics, energy was equal to kBT. So we had dN was equal to 4 pi frequency squared d nu. That was where we were starting with wavelengths that were encapsulated in a three-dimensional box and figuring out how many different m values that we could have. Okay, so we're going to reuse all that stuff. Where we're going to differ between Rayleigh-James and Planck is for the Rayleigh-James, we used Newtonian physics, which said that our energy is equal kBT, or that our, to be a little bit more specific, our average energy. So have you guys seen this used before? This is equal to the average. It's a symbol that means average, right? Another one that sometimes you'll, if you're taking statistics, you'll see used for average is like X bar. That gets used for average too, but it also gets used in vectors to denote a vector. And because in quantum, there's additional ways of doing these things that involve vectors, we are not going to be using that at all. Right? That will just complicate matters. So when we're talking about averages, it's going to be the sort of that greater than, less than bracket to mean average. Okay? Okay. So, is that all we're going to use? Yeah. So this was Rayleigh-James. That is what we use for our energy. What Planck did was he said, well, let's try energy being quantized. So instead of energy having any possible value, we're going to try having energy be in a quantized state. So the energy of a particular quantum state is equal nh nu, where n is equal to 0, 1, 2, 3, dot, 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 some integer starting at 0. Now what that means is that for the average value, the average energy would then be the population of each state. So what percentage occupies each one of these states times the energy of each one of those states added together, right? And then, so it's sort of the weighted average of those populations. So the way that we would do a weighted average is we would take the sum of all of the states, so the sum of all values for n going all the way up into infinity, right? So all possible values of the energy of any given state times the distribution. And so the distribution we're going to use is the Maxwell-Boltzmann distribution, which is essentially the distribution of the energies of molecules in the gas phase. So this would be negative En over kBT. Oh, not kBT, lower T, kB temperature. So the Boltzmann distribution, and this is one that we derived from scratch in 401, so in the other echem class. is essentially E to the minus E over K dt. Right, that's essentially the distribution. So we're taking the energy of a particular state times the probability or the weight of that particular state. We're going to divide those by the total sum of the probabilities of all the states. Okay, so essentially that's just a way of doing a weighted average. So this would be, essentially we're taking the value divided by, or times the probability of that value, and then just adding all those values together. Okay? So, if we're using En is equal to NH nu, then we can replace wherever we see En with that value. So this would be equal to the sum of all of our states of NH nu e to the minus NH nu over KBT divided by the sum n of e to the minus NH nu KBT. So if we illustrate what the first couple of those look like, right? Because we're going off to infinity, we can sort of do the dot, 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 keep going. This, we can fill in the first couple of values. And so if we plug in 0 for n, then this first term here, this is 0 times something else. The first term, where n is equal to 0, on the numerator on top, we get a 0, right? Plus the second value is if we plug a 1 in for n, so that'll be 1 times h nu e to the minus 1 h nu divided by Boltzmann's constant times temperature. This would be plus, and then if we try n is equal to 2 h nu e to the minus 2 h nu Boltzmann's constant times temperature plus, right, dot, dot, dot. We can do 3, 4, 5, 6, all the way up to infinity, right? Essentially, that's how the pattern is laying out. So that's the pattern for the numerator. The pattern for the denominator, if we plug a 0 in for n, then this is e raised to the 0. E raised to the 0 is 1. So our first value is just going to be 1. Plus, if we now plug a 1 in for n, then this would be e to the minus 1 h nu divided by kBt plus, and then e, if we plug in a 2 for n, this would be e to the minus 2 h nu divided by kBt plus dot, dot, dot. You guys good with that so far? Yeah? Okay. Now, we can pull out, if you look at the top, or actually, sorry, we can simplify this a little bit so that we don't have to keep writing e raised to the h nu and all that sort of stuff. We can say, we're going to let x equal e to the minus h nu over k bt. Right, so then we can express our average energy as wherever we see e to the h nu divided by kBt, or including the minus, we can just replace that with x. So this would be, it's equal to 0 plus h nu x plus, then it should be 2, yeah. 2 h nu x squared plus 3 h nu x to the third power. Right, because one of the rules of exponents is say e raised to the 2 times e to the x is equal to e to the 2x. Right, so if we do this squaring, this would be, this right here is the same as e to the minus 2h nu over k b t. It's a mathematical trick. You okay with that? Yes, no? Okay. On the bottom, we essentially have, where am I at? One plus x squared plus x to the third, dot, dot, dot. Now we have, if you look up top, this 0 we can just drop it, right? 0 plus anything, so we can just get rid of it. We have this repeating pattern of h nu x that we can pull out. And so we can actually rewrite this as h nu x times 1 plus 2x plus 3x squared plus dot dot dot, and then on the bottom we have 1 plus x squared plus dot dot dot. Again, the purpose of me showing you all this is not so that you can necessarily do this derivation from scratch. It's so that when you're looking through the book and it says magic happens, this is where the Planck's constant, this is Planck's law. This is showing you where it comes from. Okay, not so that you can derive it from scratch, but so that you know where it comes from. Okay. So there's actually a nice mathematical thing that will, a trick that will allow us to sort this out, to simplify it quite a bit. 1 minus x raised to the negative n is equal to 1 plus nx plus n plus 1 over 2 factorial x squared plus n times n plus 1 times n plus 2 over 3 factorial x to the third. Now, might look a little tricky as to why the heck are we doing that, right? But if you look, we have, this here is n. Well, we have a constant times x. The constant goes up by 1 times x. The constant goes up by another 1 times x. And if you look at this value here, it's increasing by 1 each time. Right, we're multiplying it by 1 bigger. And then we have the x, then it's x squared, x to the third, and over here we're starting out as 1, then plus x squared, plus x to the third. So we have, if you ignore the factorial and all that, we have that pattern of x squared, x to the third. So this might be useful. If we take it divided by itself, right, if we use different n values to the top and the bottom, these factorials, they're going to cancel each other out. Okay? So what we can do is simplify our life a little bit and say E is equal, you can see at the top, this one is growing, and this one stays as being 1. Alright, so for the top value, the N is going to start out at 2. For the bottom, it starts out at 1. And then what that means is that the top value is always going to be 1 higher than the bottom value, and so they divide and cancel out to end up giving you this pattern of 1, 2, 3, 4, 5. Okay, so if we use this as 1 minus x to the negative 2 divided by 1 minus x to the negative 1, that returns this pattern. Well, sorry. That returns the pattern that's within the parentheses. We need to have this h nu x out in front. Because this is the pattern for this value, it works out to give you the same equation. If you're not 100% sure, or if you doubt it, you can actually try plugging in the numbers, and you'll see that it cancels out to this gives us this pattern. Okay, it's one of those numerical expansions that can simplify our life a little bit. It's called one of the geometric series. Make our life a little bit easier. Okay, so if we have something raised to a negative exponent, it's the same as taking the reciprocal, putting it on bottom, and getting rid of the negative. So this is equal h nu x 1 minus x to the first divided by 1 minus x to the second. And that's just one of the things you get when you have exponents raised to a negative value. Okay? We have this divided by the same thing to the second power, so one of them cancels out. This will give h nu x divided by 1 minus x. Now we can use another useful trick. So we're going to use that x over 1 minus x. We can also take this and divide everything by x. Right, so if we divide the whole thing by another set of x's, or divide it, well, essentially divide each value by x, we'd end up getting 1 over x minus 1. Right, you end up getting the same value. So essentially it's taking this and multiplying it by x over x. So multiplying it by 1, you end up with this. What that does for us is instead of having x in 2 locations, we have x in 1 location. Right? And what that will do is when we're trying to interpret the results, it'll make it so that we only have to look at one spot instead of trying to mentally visualize how it's interacting in 2 different locations. So if we use this, then this becomes h nu over 1 over x minus 1. Okay, if we remember what our x was, we can plug this back in, and that gives us our average energy is equal 8, let me make that a little bit better writing, h nu over 1 over, our x value was e to the minus h nu divided by ABT, right, and then minus 1. Now we have this one to the negative exponent, right, 1 over something raised to a negative exponent. We can take the reciprocal of it and get rid of the negative. So this would be equal h nu divided by just E H new KBT minus 1. Okay. So, why did we do all that? Because previously we had to use the average energy and add temperature in one location. Now we have the average energy, temperature in one location. So we can now figure out how the average energy moves with temperature. Right? That's the entire purpose of what we just did. To figure out how the average energy changes with temperature. And then we're going to do the exact same thing that we did with the Riley-James, except instead of using this for the average temperature, or the average energy at a particular temperature, we're going to use this relationship between average energy and temperature. Okay, and then we're just going to carry on the derivation like before, this being the only modification that we're going to make. Okay? So, you guys have all of this stuff up till here. Yeah? Okay. Okay. So, the next step after this that we did with the Riley-James was we found dE, the frequency. Right, that was the next step in the previous derivation. And that was essentially equal to our average energy times the density of states d nu. Right, so in the previous one we had plugged this one in for the average energy. Now we're going to plug this in. So our new one, this would be H nu over E H nu KBT minus 1, capital T. Okay, that is our E. And then our N value. And then if you remember from previous, we had said that this d nu over this d nu, they cancel each other out. Right? So we end up with this times 4 pi frequency squared. Oh. So, if someone is observant, they can get some points.
On the board.
There is an error on the board. So look through your previous notes. What did we have at the previous step? I am missing something on the equation that I got. This here is the average energy, and then the next step, we have average energy times something. Some stuff that we're missing out. Nope. It was d nu over d nu. Those two parts cancel out. It should be on the part of your notes that has this part, starting out the equation.
Is it from this class or last class?
Last class.
Oh, divided by CQ.
There's a C cubed in there, there's another part too.
Oh, let's go.
Hmm?
L cube.
Yeah, L cubed and C cubed. Yeah, so this should be, with L cubed, C cubed. Okay, bonus point. I'll mark you down. Okay, so the next step was instead of looking, energy, per frequency, it was, the energy density, which was energy per unit volume. So we now look at du frequency, which is essentially dE over V d nu. So that would be what we had before times the volume, and if you remember, we were talking about a cube with all the lengths being L. So essentially it's what we had before times 1 over L cubed. So that's, so as I do this, I'm gonna combine my frequency squared here with my frequency up top. So this is 4 pi h nu to the third, L to the third, over E h nu kBt minus 1, and then C cubed. Okay, just like before, we got L to the third up top and below. So this would give us 4 pi h. I'm going to pull all my constants to one side and then have that times the stuff that has a frequency in it. Okay.
Oh, you pulled H twice.
Oh. That I did. Another bonus point. Hmm? Okay, yet again, another one. Okay. Okay, so, if you recall, previously at this point we had said, when we were doing our initial derivation, we were only looking at the positive amplitudes. We then included the negative amplitudes by multiplying everything by 2, right? So we're gonna do that same part. We're gonna take everything and multiply by 2 to account for both the positive and the negative amplitudes, right? So we're gonna take this whole thing times 2, because that takes care of both the positive wave and the negative wave. So we would have equaling 8 pi h, frequency to the third power, C, no, I want to keep the, So now what we're gonna do is see how this plays out. So this is our equation for how the energy is changing. What we want is as this equation, as the wavelength goes to infinity, we should get back the Rayleigh-James equation. As wavelength goes to 0, we should get 0. So what we can do is convert this into the form that is using wavelength as opposed to the form that's using frequency, right? To do that, we can take the frequency that's up here. If you remember wavelength, so our speed of light is equal to the frequency times the wavelength, which means that our wavelength is equal to c over frequency. Frequency. There we go. C over frequency. Okay, so we can take this essentially is over wavelength to the third power. This d frequency, to turn it into d wavelength, if we take what is it? Take the derivative of this with respect to take frequency, which would be c over lambda. We take the derivative of this with respect to wavelength to do the conversion. We find that the frequency should be, because this is on the bottom, the negative of c over the wavelength squared d wavelength. Okay, so when we move this to the other side, to come up with the equation that we're going to end up being that we will end up graphing, we have this additional term that we need to use because we are switching from frequency to wavelength. So our equation would be not mu, u wavelength would be 8 pi h over wavelength cubed, and that will take care of this part, right? 1 over e hc over lambda k bt minus 1. And then we need that negative c over lambda squared to be in there as well. Okay, so the negative, we can actually drop it because that is just which direction the light is coming out, and because we're looking at it radiating from all directions, that negative sign can be ignored. So we can re-express this as, let's see, 8 pi over 8c, and to the fifth power, 1 over e hc over lambda k bt minus 1. Okay, and I drop that negative sign from the c because all it means is a reflection on the graph. So reflecting it from the negative direction to the positive direction, we end up getting the same thing. We could have the negative in there, it would just be a difference of where you're graphing. Okay, so this here, I guess technically it should be a capital P because it's a person's name, long Okay, so now what we're gonna do is we're gonna check, does it fit our two criteria that we have, right? So at wavelength going to 0, does this go to 0? And at wavelength going to infinity, we need to get back our Riley-James equation. Okay, and our Riley-James is, we're trying to get this one. Okay? Okay. So the difficult being figuring out how this one changes with wavelength, right? It's e to the exponent, can be a little bit difficult. We can use the Taylor's series expansion, which is used to expand e to the x is equal to 1 plus x plus x squared over 2 factorial plus x to the third over 3 factorial plus dot dot dot. Right, keeps going out. Now what this would mean is if instead of using x, we can see our wavelength is on the bottom of the exponent, not on the top. We can also use e to the 1 over x, which is essentially just taking wherever we see x here and doing 1 over x. So that would be equals 1 plus 1 over x plus 1 over x squared over 2 factorial plus 1 over x to the third power 3 factorial plus dot dot dot. Okay. So we can look to see, I guess, the limit as x goes to, let's do 0 first, of e to the 1 over x. Right, this one, so if we plug in 0 here, that's e raised to infinity, right, which should give us infinity. Right, so what that means is as x goes to 0, or as what's going to be our wavelength goes toward 0, this e term goes to infinity. So what's right here, this goes into infinity as wavelength goes to 0. So well, we can use that space. So if we replace this e with infinity, we can see that as wavelength goes towards 0, our equation becomes 8 pi hc over 0 to the 5th power 1 over infinity minus 1. So the question then is, does this go to infinity faster than that one goes to infinity? Right? And the answer is the e raised to 0, or raised to a number that's going to 0, goes to infinity faster than lambda to the 5th power. Essentially, x to the 5th goes to 0 slower than x to the 0, or sorry, than e to 0 goes to infinity. Right? This term gets smaller, slower, then that term gets bigger.
E to the 1 over 0.
Hmm?
E to the
Oh, yes. 1 over 0, yeah. Okay. So, what essentially this means is that this goes to 0, right? Which checks out with our first thing. This is where the Rayleigh-James equation failed, right? Was at short wavelengths, it predicted an infinite amount of energy. What we get here is that at short wavelengths, energy drops to 0. So we no longer have the ultraviolet catastrophe of at short wavelengths, infinite energy is coming off. In fact, here the energy is going to 0.
So how does it go to 0 9 infinity? It's like, okay, so the first term, 8 pi 8c over 0 goes to infinity, right?
This
So
goes to infinity.
infinity times 1 over infinity, which is 0. So infinity times 0 is 0. Oh yeah, it is.
Yeah.
I'm sorry.
The question then becomes, does this go to infinity faster than this 1 over infinity? Not all infinities are the same. Some of them go towards high values faster. Exponent, anything in the exponent goes faster than something raised to the 5th power. Right? Essentially, it's which one reaches the large value first. Does this one go to complete 0 before this one goes to infinity? And this one is faster in changing than this one. And so when you put them over each other, this term here, 1 over this infinity wins out over the growth of this, which would end up being infinity. Okay, so this ends up going to 0. If you're not 100% sure on it, what I would suggest doing, go into Excel, write out a function here. So essentially write out, and you can leave off all these constants, right? Just do 1 over one of some other cell raised to the 5th power times 1 over, as this is going to infinity, the minus 1 becomes negligible. So you just 1 over e raised to 1 over that number. So essentially plot, or do 1 over x times 1 over e to the negative x or 1 over x. And then just take your x value and ramp it up and see, does the number get bigger or does it get smaller? And you'll find that it gets smaller. Okay, so if you graph that, it ends up going towards 0. Okay, so this one here works out. The other one is, do we get back this equation? Which, I don't know, should be pretty cool if we do, right? So if we plug in infinity, really big numbers for x, what do we end up getting? So if we look here, what happens when we start plugging in really large values for x? This term here, the 1 over x, starts going to 0. These terms start going to 0 a lot faster because it's 1 over and even closer to 0 going to a power, and then it's getting divided by a factorial. So essentially, we can say this is approximately equal to 1 plus 1 over x. Right? These other terms go to 0 a lot faster than the 1 over x does. Okay? So we can approximate this with 1 over, 1 plus the exponent. So that means the limit as wavelength goes, gets really big, is that this is equal to 8 pi hc over our wavelength to the 5th power 1 over, and then I'm going to use what we have here for our e, which is 1 plus what the exponent, or 1 plus what we had for the exponent, which is hc over lambda kbt, right, and then minus 1. So this part here, right, that is what the e raised to the 1 over x turns into as your wavelengths get really big. You have a plus 1 here, a minus 1 here. Those two cancel each other out. You have hc divided by something, so it's the same thing as taking the reciprocal. So this is 8 pi hc lambda to the 5th power times hc lambda kBT HC's cancel out. This lambda will cancel out one of those. So you end up with 8 pi kBT over lambda to the 4th power, which is magic. You get back the Rayleigh-James equation. If you plot this out, the equation here right? We plot that out, your versus the experimental values, they sit right on top of each other. So this matches black body radiation to the T. Does it perfectly well. Okay, so this sort of gives credence to the idea of there being quantized energy levels. So this is one sort of, I don't know, peg in the wall or whatever you want to call it.
The
Okay.
big assumption is like the n has to be integers.
N has to be an integer.
Is that very nature or?
Hmm? We will see how this solves all those. So we came up with 4 problems that classical mechanics couldn't explain. And I'm going to show you how each one, through a derivation, it solves all those problems by saying that energy is quantized. Once we start getting down to very low, or once we start looking at small values, things end up becoming quantized. Okay, so I promise that each time we're going to try to take a break. We just finished a fairly lengthy derivation. Time to let the brain cool a bit, and we'll come back in about 5 minutes.